Okay, so this is a status update on LIGO's 5th science run, which is still in progress. So unfortunately, I can't tell you that we've seen anything yet or tell you final results. But this is to whet your appetite. Okay, so this is the one-page slide on LIGO, assuming that most people here know about LIGO. But LIGO is 3 interferometers at 2 different sites in the United States. One in Hanford, Washington, and one in Livingston, Louisiana. You can see they're very similar installations, but quite different terrain. This is a timeline. I'm going to give some perspective for S5. So this is a timeline of LIGO's development to date. So you can see way back here, first lock in 2000. And then since then, there's been a progression of engineering runs, denoted E2, E3, etc. And then starting in, I think, August of 2002, we started with the first science runs of LIGO. And those were interspersed with engineering runs and commissioning periods as the detectors continued to be improved up until where we find ourselves now in the middle of the S5 run. And you can see there's just a benchmark number here for sensitivity, and you can see that march along as we go in time. So a little bit more information on the science runs up till now. So they started rather short, only a 17-day science run for S1. I can't remember the number offhand, but a good fraction of this, at least in the burst search, is actually thrown out because of poor data quality and low duty cycle. And not only has the sensitivity improved, but the duty cycle has also improved throughout these runs. And you can see sort of one a year almost up until the 4th science run. And this is a picture of the strain sensitivity of the LIGO detectors through that time. So the cyan curve here is the S1 curve, and you can see how it's improving by orders of magnitude through time until now this red curve here. I forget which of the LIGO detectors. This is sort of a best LIGO detector in each science run picture. Is sitting very close to this reference curve, this black line that comes from the science requirement document. So at the end of S4, in preparation for S5, the NSF recognized that LIGO had reached its agreed upon design sensitivity, which is an integrated RMS strain of 10 to the minus 21, integrated over a band of at least 100 hertz. At that point, in November of 2006, LIGO started its 5th science run. And the goal there is now to accumulate 1 year of coincident science data at, or actually now above, that design sensitivity. Hanford started collecting data on November 4th, and then Livingston joined 10 days later. You expect to last 1.5 to 2 years long in order to get that 1 year of coincident data. And the schedule permits some periods of minor interruptions for maintenance and commissioning periods for improvement. And this is quite a big departure from the previous science runs. It's the first time we've done something such a long time scale. So before, we didn't have to worry about the interferometer changing throughout the science run very much. It was a static instrument. Now, from the point of view of data analysis, it's a much more complex task because we have to monitor this instrument as it changes over the course of a couple of years. And so here's a very nice plot. This is the sensitivities, I think, in June of the 3 LIGO detectors at one point during the S5 run. And you can see that they're all beautifully followed along this reference curve. The bottom, I think the canonical choice of colors in LIGO now is red for the Hanford 4-kilometer detector, blue for the Hanford 2-kilometer detector, and green for the Livingston 4K detector. And just to give a slightly closer in view of what's going on there, there's this really nice noise budget that's been produced, and this is actually automatically produced, I think, at least once a day, if not twice a day, and publicly available on the LIGO website through the detector logs. And it's hard to see here, but this green dotted line is a quadrature sum of all the noise sources that show up in here. And I can read, there's a ton of them here, but some of the more primary ones are shot noise in this region, thermal noise in this region, and seismic noise in this region. And the black noise curve is the actual measured noise. There actually is a discrepancy in this region here. So That's some people have called it mystery noise, most likely due to some kind of up conversion source. And that's, I think, the focus of a lot of commissioning efforts right now. In particular, one of the canonical measures of how well LIGO is doing is the in-spiral sensitivity. And as you improve sensitivity in this lower frequency region, that number can go up quite readily. So this is one of the primary measures of the sensitivity of the instruments. It's the so-called sense-mon range. There's actually a couple different in-spiral ranges. This is the detectable range to a somewhat randomly, that's a loosely used word, oriented 1.4, 1.4 solar mass binary neutron star in-spiral. It's if it were to be detected with an SNR of at least 8. And so you can see the SI run starting back in November through to some point earlier in this month. And the sense-mon range is marching along here. These might be disconcerting, all these little dots in here, but those are periods of time when the instrument runs out of lock and it's sort of dropping down and comes back up again. And, but you'll have to trust me that most of the time is spent up here and not down here. Maybe you can see by the density of dots there. The same, actually. So there's a couple of very noticeable changes in this plot. And one of them is this first commissioning period that took place in Hanford. So both the H1 and H2 detectors underwent a week-long period of commissioning first in the run. And there's also another change very recently. There's actually a very large earthquake on, I think, Mount Rainier that knocked the interferometer back in sensitivity by a megaparsec or so. And I think that still persists to this day. There's been some recovery, but it's still not operating quite as well as it was back at that point. You can make a similar plot for the 2-kilometer detector at Hanford. Not quite as sensitive in terms of in-spiral range. You can see here it's running along 12 megaparsecs and up to near 15 megaparsecs. The 2-kilometer is roughly half that, so running along at 5. And then with the commissioning period, there was a substantial improvement in H2's performance and then marched along. H2, by the way, maybe you can tell by the slightly fewer dots down here, has been a very stable detector all along. Not quite as sensitive, but its duty cycle is extremely high. And then finally, when you get along here, not long after H1 dropped in sensitivity due to the local earthquake, H2 experienced a problem where it dropped down to a sensitivity around 2 megaparsecs for a period of a week or so. And I'll describe later on, but happily that seems to be fixed, and we're back up here now doing similar to what we were doing before. Okay, and finally, here's the similar plot for the Livingston 4K detector. As you can see that the commissioning period, actually there was some work during the commissioning period in Livingston, but it was not an official commissioning period for Livingston. But there was some minor improvement over that time. But the actual commissioning for Livingston, actually, I think it was around here. Does anybody remember the date of the Livingston commissioning? I didn't mark it. Okay, so I think it's around here somewhere. This major improvement was actually due to a stuck optic, and I'll describe more of that later on. So bad news turned into good news for us. This is a picture of what the histogram of those scatter plots looks like if you look at edge on. And so you can see here the H2 detector spent some period of time around 5 megaparsecs, and then after improvement in sensitivity jumped to around 7. And likewise, there's sort of this bimodal distribution for all three of the detectors as they underwent improvements during commissioning periods and fortunate events during S5. Here's a different take. So sensitivity and noise curves are only one measure of how well LIGO is doing. The other measure is its duty cycle. So in this case, what's plotted is cumulative observation time in what's called science mode data. So the people in the control room, there's an operator and a science monitor. It's their duty to look for good quality data and hit a button that marks this data as science quality data. And that gets marked down in the database. And what's plotted here is the cumulative science mode quality data over time over the past year, where we find ourselves today. And so you can see we're not quite 100% duty cycle. The blue curve, as I mentioned, the H2 detector is a very reliable detector. Was doing quite well, so up in the 70% duty cycle. The Hanford 4-kilometer detector not far behind it, and the Livingston detector roughly around a 60% duty cycle over the course of this year. And again, you can see some interesting events in the milestones of S5 here. The initial Hanford commissioning period where the duty cycle dropped during that week. A Livingston commissioning period where again the duty cycle dropped. The period around the time of the stuck optic that I'll describe. And then we experienced a similar event in H2 that looks like another stuck optic, and a similar solution helped things there. Here's another view of the same thing. This is duty cycle, but this in this case is a 1 week running average, a trend of duty cycle over time with the 3 detectors. And again, you have commissioning periods early on. All the same events that I just showed previously are in here. There's also this recent event, I think this, if I got this timing right, is the earthquake in Hanford causing H1 and H2 to lose sensitivity and H2 to drop out for a while. Also, at the same time, there were some power outages in the Livingston detector and a series of glitches in the Livingston detector that required us to shut down for a little bit of time to fix that. And so all 3 had this sort of loss in duty cycle very recently, but it looks like we've recovered well from that. So it's very difficult to do a single detector analysis because of all the glitches, at least for the burst and in-spiral searches. So of primary importance is the coincident data time, or network observation time. So there are also many different networks you can form with the detectors, but I put a few of them up here. In black is the triple coincident cumulative live time, so that's when all 3 detectors are operational. In magenta here is what I've labeled as 2 sites. That's where at least one of the Hanford detectors is operating in coincidence with the Livingston detector. So you have 2 independent sites taking data and are hopefully immune to environmental fluctuations. The cyan curve is when you have at least 2 detectors, so that includes triple coincident time. It also includes H1, H2 time, so 2 co-located detectors at the Hanford site when Livingston is not on. And finally, this yellowish curve here is when you have at least 1 detector operational. Not terribly useful for doing a blind search, but that's, I think, good news for astrophysically triggered searches, such as gamma ray burst searches, where if you extend this line up, I think it hits somewhere around 90%. And then here's sort of a summary view of all that. These are excluded regions, mutually exclusive numbers here. Triple coincident, we have roughly 163 days of triple coincident data for S5. If you take the 2-site coincidence data, we have now 192 days. And you can see they're all the same numbers all around here. At least 1 detector operating has 317 days and an 88% duty cycle, which I think are very good numbers. Daniel Sigg actually has at Hanford, has a script that on I think a weekly basis goes through and computes a lot of these quantities, measures of how far we're doing, how far we've gotten in S5 and how far we have to go. And this is one of the things that's produced there, and that's a prediction of how long to the end of S5. So this is saying how long till we get 1 year of coincident 2-site data. And it's projected from last week of data, the duty cycles over the last week, over the last 2 weeks, et cetera, and over the whole run. And you can see it fluctuates around there a little bit, but sometime around a little less than 2 years, 1.5 to 2 years from the start date. And this nice green bar that tells us all how far we've gotten, and we're halfway there. So it's nice to see. So you might ask, why don't we have a 100% duty cycle? And Betsy Blend at Hanford has made this nice pie chart that describes some of the details of where that lost lifetime has gone. Probably can't describe all of these things. Some things that jump out at me. Tuesday maintenance period. We set aside a set time each week to do maintenance activities. So that's this pie wedge, this sort of cyan-colored pie wedge right here. So they've identified seismic activity making it difficult to run, unaccounted for lock loss issues, a variety of random things. But in general, you see there's this nice big 76% uptime pi wedge. So as I mentioned, S5 is not an easy task. It's the first time we've tried to do this over such a long time scale. In order to do that, there's been a global run coordinator assigned. That's Vern Sandberg at Hanford. And then rotating site run coordinators that report to Vern that are tasked with these two primary goals, and that's maximizing the coincident science mode time of the analysis and maintaining optimal range and good figures of merit during that lifetime. In order to make this all work, there's an operator present in each of the two site control rooms 24 hours a day, 7 days a week. There's also a so-called science monitor present. Originally it was 24 hours a day, 7 days a week, and that's been scaled back now to, I think, 20 hours a day, 7 days a week. The science monitors are staffed by people from throughout the LIGO scientific collaboration. So people here at Caltech, and MIT, but also all the other institutions that are involved in the LIGO science collaboration, Syracuse, Milwaukee, et cetera, et cetera. And also to make this all run, there's a weekly teleconference run by Vern to talk about issues. And the goal there is to get rapid feedback from all the variety of people that are working on S5 data analysis and detector characterization back to the operators and commissioners to correct problems as soon as they develop. And I think that's actually one of the really nice things that's developed out of S5 is how fast we can turn around and solve problems. As I mentioned before, there's this 4-hour maintenance period identified on Tuesday mornings. It's actually done at the same time between sites to minimize the impact on the coincident science mode time. But unfortunately, a lot of stuff takes place during that time, and it's difficult to do work on improving the detectors when so many things are going on. So there's been some additional time, 25 hours per month, allocated for commissioning activities outside of those windows that's at the discretion of the run coordinators. And then occasional longer commissioning breaks are also taking place during S5, and you saw the result of those in the inspiral sense-mon range jumping up dramatically. So here's a picture of some of the milestones during the S5 run. Both Hanford and Livingston began taking data in November. The first Hanford inter-run commissioning period was in early to mid-February, followed by a Livingston commissioning period in April. And then May 2nd, there was an event occurred, and I'll describe it in a little bit more detail, where L1 had a mirror struck, cut off here, against an earthquake stop. And then a few days later, venting of the chamber and mechanically moving that improved the sensitivity. And then more recently, there's a strong local earthquake near Hanford on Mount Rainier that caused sensitivity drops in both H1 and H2, effectively making H2 down to less than 2 megaparsecs and requiring that it be taken out of science mode for a week. But then the same procedure, this venting procedure, also seemed to fix the H2 detector. So what is this venting procedure? It turns out, I think the hypothesis is that a passing truck caused the Y-arm input test mass in the Livingston detector to shake and get mechanically lodged against one of its earthquake stops. And to actually free it, there's various steps that are taken. Kicking on the chamber, shaking it around, eventually venting it, puffs of gas, and finally I think it was required to go in and mechanically release it. But the process of doing that actually resulted in a dramatic improvement in the low frequency sensitivity region where that mystery noise is, and therefore a corresponding increase in the inspiral range. So we lost some live time, but we really gained in sensitivity, which is very nice to see. And the thought is that Viton-tipped earthquake stops are charging the optic up when the optic is hitting against them, and that excess charge is resulting in some noise. But the venting the chamber causes, I guess at the right pressures, causes the optic to discharge. And this was applied again successfully to the H2 end Y test mass, I think, earlier this month after suffering a similar problem. And here's a nice little picture of what these look like, so you can see the earthquake stops and the little tips on them right here, right up against the optics. And contacting that. So sensitivity and duty cycle, even with those two things, are not the full story. There's actually many other figures of merit that are available in the control room in order to look at, for instance, the non-stationary data, look at the predicted range to inspirals, the RMS strain sensitivity in various bands. There's now a calibrated noise spectrum on the wall at Hanford. Also, figures of merit that are relevant to the particular searches, such as the most significant inspiral trigger in a 1-minute trend period is plotted on the screen in the control room and available actually in the detector log. The 50% amplitude required for detection of burst of various waveforms at a given pulse rate is also done for plotted as a figure of merit on the control room wall. Non-stationarity is measured, which I'll show a picture in a second, but by the glitchiness of the data, one of the burst search algorithms takes the data and tries to cluster the triggers together into groups, and it's measuring the fraction of time frequency area that's involved in clusters as a measure of non-stationarity of the data. And then also there's a variety of environmental measures, in particular looking at the band-limited seismic noise in various bands that indicate, for instance, microseismic activity, trains, logging, etc. at the sites. So here's an example screen that's available on the control room wall. So in this case, you can see the band-limited seismic noise over time. This is a 12-hour period in different bands. It's probably difficult to read there, but each one of these colors is a different band. Some of them are more attuned to microseismic activity. Some of them are more attuned to human activity. Some show up earthquakes very well. This is showing the states of the 3 detectors. So in this case, they're all working pretty well. Livingston had some up and down periods throughout the day. This is, I think, I don't see the date there, October 31st, so very recent data. And again, this is the inspiral sense-mon range over time. Here are some of the more search-specific figures of merit. Burst-mon pixel fraction, which is measuring the glitchiness and non-stationarity of the data. There's a reference line you can see there for the benefit of operators. This is the online binary inspiral search. So you can see the vertical axis here is signal-to-noise ratio, and each of these dots plots the highest signal-to-noise ratio trigger in a 1-minute period over 12 hours. So you can see that the data actually is very nice and flat, all well below this inspiral sense-mon range SNR of 8. With an occasional few events up here that could be hardware injections. It's hard to tell from this plot. In addition to the figures of merit, we also have a number of tools that are running online or with very short latency in order to provide rapid feedback to operators and commissioning teams when problems occur. This is an example case of something that occurred very recently, where the algorithm that takes a snapshot of the detector state once an hour and records all the control channels to disk was somehow overloading the system and caused glitches in the detector once an hour. And so you can see this is a plot of trigger significance seen by one of the burst search algorithms, a Klein-Avelli algorithm, as a function of time throughout a day. And you can see right here, every hour there's a pulse coming up. And that was identified as, the culprit was identified by changing that data storage to once every 3 hours, and that the corresponding plot changed to once every 3 hours. And so we were able to figure out what's going on, at least to find the smoking gun. Haven't quite solved why it was doing that yet, but it's been spread out now over time. Another tool that's been provided to follow up candidate events is this web-based tool, QScan. It basically, you give it a time at an event, such as an interesting glitch, a hardware injection, or hopefully pretty soon a possible candidate event, and it's going to go through all of the channels in the frame files, potentially all the channels in the frame files, and look for statistically significant activity in those channels around that time over time scales of, say, 1 second, 2 seconds, and 8 seconds. And that's all fully user configurable. A lot of the online analysis now automatically generate these things whenever they find an interesting event in the data. So that online binary inspiral I showed earlier, for the top, I think it's 20 loudest events per day, and each detector automatically produces a scan like this. In this case, these little bumps here, this is the gravitational wave channel, it's a spectrogram of it. These little bumps here are what's going on during these times here. And this is just a screenshot, but this is a web page, and you can scroll down and see many, many, many channels of data and what they're all doing at that time, and get pictures of time series, spectrograms, etc. Okay, so here's an example of some of the kinds of things that we're working to rapidly give feedback on. This is an example of a data corruption that occurred earlier in S5, where the data actually repeated itself. This is the gravitational wave channel. This is just some random other channel that I picked from the frame file. It's easier to see here, but this piece right here is essentially a repeat of the previous 1/16th of a second of data, which is the time scale at which chunks of data are recorded by the frame builder in LIGO. So this is the time series, and this is the corresponding frequency spectrum. This was picked up by the online binary inspiral search. These Q scans are looked at on a weekly basis by a group that has a regular meeting on Monday mornings. This was observed very readily. The follow-up identified it as a data corruption very quickly. Then people at Hanford were able to put in tests for the quality of the data. Data is actually written out in 2 different frame builders, redundant frame builders at the same time, and they're able to do checksums against the 2. And whenever there's a checksum mismatch now, that's flagged, and we have the ability to go back. We store both sets of data then, and have the ability to go back and look to see which one was corrupted, which one wasn't, and recover the good data. Here's another example of the kind of things we see during S5 that we need to deal with. So this is a coincident glitch in H1 and in H2. These are both the gravitational wave channels, and here's the corresponding time series. So they're actually very strong events. This is actually after whitening, but still very strong. And it turns out that they're associated with large transients observed in the magnetic field glitch detectors, as well as voltmeters scattered throughout the entire Hanford site. And I think, to put this in perspective, I think these fluctuations here are probably the 60 hertz magnetic field fluctuations. And this is a very large fluctuation sitting on top of that. Another example of the kind of things that we see and follow up on, in this case, a seismic disturbance. It turns out that this was not a natural one. It's a little dark, but there's a little forklift here, and I think this was identified with the forklift hitting the ground. So this is, again, the gravitational wave channel and gravitational wave channel spectrogram. And this is a spectrogram of one of the environmental channels. In this case, an accelerometer sitting on one of the input or output tables of the interferometer. And this is a measure of significance here. Roughly, this is squared SNR, so this is actually a very strong event. Okay, some other types of things that have affected the S5 run. One is wind activity, in particular at Hanford. All of the data is recorded as trend files, so you see along the bottom here trend file information on wind velocities at the various Hanford stations, mid-Y station, mid-X station, EY, EX, corner station. And up on top you see the SenseMon performance, and you can see during this period of high wind, the red and blue traces, the 2 detectors had a hard time staying in lock and also had some decreased sensitivity. During the same week, you can also look at microseismic activity. This is, if you looked at a spectrogram of the seismic fluctuations, you would find a peak at around, I think, 0.2 hertz or so, which is associated with ocean wave activity. And this increases and decreases over time, and in particular in Livingston, it seems to have an effect on our sensitivity as well. So you can see in times of increased microseismic activity, the Livingston detector has a harder time. Other types of seismic disturbances. Livingston had construction of a science outreach center for the early part of S5. I think it's almost complete. This is very recently. This is the final pieces going up on the outside. The major construction is now complete. So hopefully that means that we'll have an improvement in duty cycle and sensitivity, and also a very nice facility for doing outreach at Livingston. So I've only mentioned a few of the zoo of things that we have to worry about for S5. And this is a snapshot of the defined data quality flags as of today. I'm not going to go through them all, just but to highlight a few of them. For instance, wind over 30 miles per hour. There's actually a few of these ones, but 60 seconds, 120 seconds, et cetera, prior to a lock loss. There's now seismic flags available. Our calibration apparently drops out occasionally, so we flag those times. H2 not locked and H1 not locked. We found that when the H1 detector is operating but the H2 is swinging, there can be scattering between the two detectors, where H1 light scatters off of H2 and back into H1 again, giving rise to some nice, in the time frequency plane, little arches. And as a result, we define these data quality flags, and that actually probably will have an impact until we figure out how to deal with that data on the amount of coincident data that we can analyze. We also have a variety of overflow flags in here, so when there's saturations in the instrument, these flags typically indicate that. Another important aspect of the S5 run are hardware injections. We've been doing these actually for all science runs. A variety of waveforms are injected, so binary neutron star and binary black hole in-spiral waveforms are injected. These are physically injected by pushing on the test masses. I didn't mention it here, but there's also now a photon calibrator that has the capability of pushing on the test masses. The burst search is injecting a variety of waveforms, Gaussians, sinusoidal Gaussians, cosmic stream cusps, etc. We're also injecting, for short periods of time, stochastic backgrounds, and then over longer periods of time, simulated pulsar signals are injected into the instruments. This is just an example case of what it looks like when you look at one of these hardware injections. In this case, 1.4 solar mass in-spiral at a distance of 5 megaparsecs. So you get this beautiful chirp in the H1 detector and the H2 detector. And one nice thing about hardware injections, we can also test the quality of our reconstruction of calibrated time domain data. In particular, I can take the subtraction of these two things. I'm not showing it here, but get something that's consistent with noise. And that tells us a lot, I think, about how well we're doing at calibrating our data. Okay, so to end with, I just wanted to show some pictures of where we think the data analysis will, where we expect our results to be for data analysis for the 4 search groups in LIGO at the end of the S5 run. These are all predicted results. The actual results aren't available yet, although I should say that there's a LSC meeting coming up this weekend, and a number of the search groups are going to be presenting early results from the first part of S5 at that meeting, and hopefully some of those will lead to publication very soon. Just to give you a picture where the stochastic result falls, so this dotted line right here is the expected sensitivity based on the LIGO design curve, which is essentially the same as the S5 curve for the S5 run at 1 year of data. You can see that it's now, so here are the previous results up to S4, and here you see that we're just hitting the Big Bang nucleosynthesis limit. It's a snapshot of the big picture from the pulsar search. So here is the expected sensitivity of the LIGO detectors from S5 after 1 year of integration, again based on the design sensitivity, which is similar to the S5 spectrum. In particular, you'll note that the crab is actually going to be above where we think we will lie at the end of S5. That's the spin down limit for the crab, assuming that all the spin down is due to gravitational wave emission, And matter of fact, even before the S5 is finished, we should pass that, and I think we're probably around that point right now. I think there's some pulsar people in the audience, but they can point out which is the pulsar that has the best constrained ellipticity, you know? Is it on here? Not on here, okay. Are hard to identify.
Yeah, it's a random pulsar around a couple hundred hertz.
Okay. Well, I cut that slide, but so the crab, I think, is one that is interesting, but there's also one that gives a very tight constraint on ellipticity. This is what we expect from the burst search. So both the S4 and S5 results are not released yet, but what's put on here is the results from the S1 and the S2 searches. This is for injected sinusoidal Gaussian waveforms, which is one of the sets of waveforms we use to characterize the search. Looks like something, yeah. The strength of signals for the burst search are characterized by this quantity, which is something that has units of strain per root hertz, just like the power spectral density, or amplitude spectral density. And so what's plotted here is rate in events per day versus this characteristic amplitude, and the region above these curves, above and to the right, is excluded at a 90% confidence level. So as your lifetime increases, you can start pushing down this way to lower and lower rates. And so the 1 year lifetime for S5 is what really brings us down here. And then as the sensitivity of the search increases, as the detector improves, as the algorithms improve, as our ability to exclude glitches improves, we start pushing in this direction here. And so you can see that from S1 to S2, there's been dramatic improvement. S4 is expected to lie around somewhere around here, and S5 around here in the region from 10 to the minus 21 down to 10 to the minus 22. And finally, just a snapshot of what we might expect from the in-spiral search. So this is based on the first 3 months of S5. I think these are 1 sigma error bars for the predicted detectable range to, in this case, optimally oriented. That's what the word horizon means, which is different from the previous plot I showed you. Optimally oriented binary black holes as a function of their mass. And so you can see that masses around 25 solar masses sit such that they fall in the LIGO sweet spot more than other masses do. And we have, one nice thing about the binary black hole search is that the numbers are extremely large, out to hundreds of megaparsecs. So what about after S5? Here's a simplified timeline. Here's the end of S5. Planning is now already well underway for both an enhanced LIGO and advanced LIGO. Advanced LIGO construction has a period of time before it actually begins installation, and during that period of time, it's expected to spend a couple of years of improvements to the initial LIGO detectors, using a lot of the technology that's going to be applied in advanced LIGO and testing it out, and then have a period of time denoted by S6 that ends when the first IFO is decommissioned and installation of advanced LIGO begins. The nice numbers here, though, is that in this time period here for enhanced LIGO, we're hoping for something like a factor of 2 increase in strain sensitivity. But remember that volume is h cubed, so that's a factor of 8 increase in the volume that LIGO is sensitive to. And then for advanced LIGO, roughly a factor of 10 increase in sensitivity, so a factor of 1,000 increase in volume sensitivity relative to initial LIGO. And so that's just the nice picture of what's to come in the future. You can see the initial LIGO is this sphere here. Enhanced LIGO now has been added to this picture, and then advanced LIGO way out here at the edges. That's it.